welcome to the first episode of Adventures in OS Development. My name is George, and we're about to start a journey together to build an operating system from scratch, mostly in C. We're going to write every piece of code the computer will execute from the moment the BIOS finds our operating system on the drive. If you want to follow along, you can make your own one too, and you might even want to make some fun customizations. GeorgeOS isn't going to be efficient or secure, at least not yet. It's optimized for fun and understandability. We're going to start with the bootloader, get it to load our operating system from disk, and then start building that operating system bit by bit. But first, what is an operating system? We all know about Windows, Linux, and Mac OS, but what is the minimal essence that defines one? There are probably hundreds of different opinions out there about exactly what defines an operating system, but there are some key characteristics I think we can agree on. It boots the computer. It has to be able to take the computer from just switched on to being ready to run the user's software. It provides services to the programs you want to run. Programs need to be able to do things like printing to a screen and reading from the keyboard and opening files. And they don't want to have to know what kind of video card you have or what kind of hard drive or what file system you have on that hard drive. So the operating system provides a layer of abstraction and provides a service like, open a file please. And it needs to have a shell. That's the program that lets you choose and run other programs. For example, in DOS, it's called command.com. There are also graphical shells, of course, but we'll just ignore those for now. This is a text-based operating system. And in most cases, an operating system will come with some basic utilities to do simple things like copy a file, edit a file, format a drive. These aren't necessarily part of an operating system, but they're things that we tend to perceive as being an integral part of it. There are some other things that all modern operating systems do, memory management and multitasking and things, but we can and will build an operating system that doesn't need to do those things. It's going to be simpler than that, so we're not going to go there. All right then, we're nearly ready to get started. The first thing we have to do is to write a bootloader. But so that we can understand the role of the bootloader, let's just think about what happens when the computer first turns on. We're talking about x86-based computers here. That means pretty much anything that can run Windows or DOS. Now, the computer has to start somewhere, and x86 processors are hardwired to start executing instructions at a particular memory address, FFF0:0. That's a funny looking memory address because it's a real mode address. We're going to get very familiar with them later on, but I'm going to hold off for now on explaining anything about hexadecimal math or real mode segmentation. Anyway though, that memory address is where the flash or EEPROM memory of the BIOS is mapped, that chip you see highlighted there. The code inside that chip initializes the hardware at the lowest level and then starts looking in the disk drives, floppy and hard drives, for an operating system. What it's looking for is a so-called magic number, AA55, at the end of the first sector. If it finds that, then it knows it's found a boot sector, and it will copy that sector into memory and execute it. We need to write one of those, and we need to make sure that it's in the first sector of our disk. We're going to write that bootloader in assembly, and all it's going to do is print out the word hi. Okay, so now we're looking at an empty workspace in VS Code, the editor I've chosen to use. Let's make a file in which to write our bootloader. I'm going to call it bootload.asm. The first thing we need to do is tell our assembler where the origin address is. That is, the memory address where the first instruction will be put. In this case, we know that the BIOS is going to copy our bootloader into memory address OX7C00. So that's what we need to write. Org 7C00. The assembler needs to know this so that when we tell it later to reference a variable or something like that, it can calculate the actual memory address to put in that instruction. We'll talk about that more later. Now we can write some real assembly code. And the first thing we're going to try to do is write the letter H to the screen. To write to the screen, we can use the BIOS. The BIOS is more than just something that finds and starts our operating system. It also provides a bunch of services of its own that we can use to perform low-level tasks. And one of those is printing characters to the screen. There are many good online resources that tell us about these BIOS services. The most comprehensive is called Ralph Brown's Interrupts List, and we'll use that. We call BIOS services by invoking a software interrupt. An interrupt causes the CPU to stop what it's doing and execute a predefined piece of code. Hardware interrupts are used to handle events such as a keystroke, time passing, etc. But interrupts can also just be called directly by using the int instruction, and those are called software interrupts, and that's what we're going to do. So there tends to be one interrupt per major area of functionality in the BIOS, and a number of different function codes per interrupt. The video ones all live under interrupt 10H. That means 10 in hexadecimal. And the function that's really interesting to us is called teletype output. So that's function code 0EH, or just E. And the documentation here tells us what we need to do to call it. We need to put 0EH in the AH register. So that's the function code. And we need to put the character that we want to write to the screen in the AL register, and a page number in the BH register. And that foreground color, we don't need that because we're not running in graphics mode, we're running in text mode. So to copy stuff to a register, we need to use the move instruction, MOV. So we're going to type in move AH OXOE, move AL. This is where we put the letter we want to write. And we could put in the ASCII character code, OX60, for example. But conveniently, we can actually put in the character itself in single quotes, and our assembler will figure it out for us. So let's write H. And in the BH register, we need to put the page number, and that is simply going to be 0. Now finally, to actually invoke the thing, we need to call interrupt 10. So we're going to say int 10h. Believe it or not, that's kind of it. We have a piece of assembly code that will print an H to the screen using a BIOS function. We better add the I as well. Our documentation tells us that this BIOS function will return nothing, and that means it should leave the registers we've already set alone. So all we need to do is change the value in AL and call the interrupt again. Let's just tidy it up a little bit so that things are a bit clearer. One more thing. We don't want the computer to just keep running whatever is in memory after our code. It doesn't know when it's reached the end of our bootloader. So we can prevent that by making our last instruction be an endless loop, a jump to its own location. To do that, we can just type JMP for jump $sign. The $sign is a special symbol that references the memory address of the current instruction, which is the jump itself. So that will just put the CPU into an endless loop once it gets to the end of our code and guarantees it's not going to go and do anything strange. Let's see if we can assemble this into machine code now. We're going to use nasm, aka the net-wide assembler. Let's type in nasm-0, which means don't optimize our code, because that way it'll be easier to understand it because it's not getting changed. -fbin, which will produce a flat binary file without any special headers or anything that the CPU won't understand. Output file, bootload.bin. And our input file is bootload.asm. Done. Let's have a look. Our bootload.bin file has been created. It's 15 bytes long, very small. And if we want to look inside it, there's a couple of different ways we can do it. We can use ndisasm, and that will disassemble our binary file by parsing the instructions inside it and give us a listing much like what we wrote in the first place. We can see the hex value E being put into AH register and 0 into BH, etc. And we can see our jump at the end. It might also pay to have a look with hex dump. Hex dump just shows us all the raw bytes of the file, and we can see those matching up with the bytes that are shown in ndisasm. And interestingly, hex dump can also show us an ASCII representation of those bytes, and we can see that the only printable bytes in the file are the H and the I that we wrote. So is it a bootloader now? Maybe, but it's not a valid boot sector yet. We need to meet two new requirements. Firstly, a sector is 512 bytes, so our boot sector has to be 512 bytes in size. And as we mentioned before, it has to end with the word OXAA55, a word being a 2-byte number in this case. These 2 bytes are the magic number that the BIOS looks for to tell if it's found a boot sector. And without those, it just won't think the driver's bootable at all. So since our boot sector is only 15 bytes long, we're going to need to add some padding. We could just write a bunch of padding by adding no-op instructions or something like that, but we'd need to write an awful lot of them, and there is a better way. There's a directive called times that lets us multiply things. And furthermore, remember the $ we used in jump $? There's another one called $, which refers to the address of the first instruction in our file. So the difference between $ and $, is the length of our bootloader. So let's type in times 512 minus $, no-op. Now we're going to get exactly the right number of no-op instructions, which is byte 90, at the end of our file to make it 512 bytes. Let's have a look. Our file is now 512 bytes long, and if we look at the output from hex dump, we can see a whole bunch of 90s in there. And that is the opcode for the no-op instruction we wrote. You can use anything you like as that filler byte, and zeros are quite common. It's never going to be executed, but no-op is quite useful because it's easy to see in a disassembled output, and it's easy to filter out with grep, and it's guaranteed not to confuse the disassembler. Of course, this isn't still quite what we need. Let's change this to a 510 and add in our magic number. The way we can do that is using the DW directive, define word. So we'll type in OXAA55 and have another look in hexdump. Hexdump skips all the lines that are identical. So now we can see right at the end of our file, 55 and AA. That's in backwards order because the x86 processors use little endian byte ordering. That just means that when a number is represented in memory or in a file, the least significant parts of that number come first, which is the opposite of the way that we humans naturally write numbers. And that's for some historical reasons that I won't get into right now. If we want to use in disasm, we're going to see that there's a whole lot of no-ops in the file. And so the best thing to do is probably just filter them out with grep. grep-v no-op. And now we can see a nice listing of what's in the file. And the last one thing we see is address 1FF, which is the 511th byte. So at last we've got a valid boot sector. Let's try and run it. If it's a valid boot sector, then it's also a valid floppy image because a floppy image is just the raw bytes of a floppy disk. It's a small floppy image, but it's still a floppy image. And so we can just point qemu straight at it. So qemu system i386 dash drive file equals our bootload file. Format equals raw. Index equals 0 because it's the first drive. And if equals floppy. We're emulating a floppy drive. And if we run that, then right after booting from floppy, we see the word hi. And that has come from our bootloader. So the BIOS has copied our boot sector into memory, jumped to the start of it. Our code has executed and called the BIOS function to write an H, to write an I. And now it's sitting in an endless loop. Just for fun, let's see what would happen if we didn't have the right magic number at the end of our file. What if we just got rid of it and had a file full of no-ops instead? As you can see, after saying booting from floppy, qemu has now concluded that there isn't a bootable floppy disk because that magic number is what it uses to tell. I'm going to finish with a little glimpse of what's a few steps ahead, and that's what you're looking at. So thank you for watching. Next time, we'll be able to cover a lot more ground. We'll learn how to call functions in ASM, and we'll start to make our bootloader read from the disk. I think we'll be able to do quite a bit more coding next time, because in this video, I had a huge amount of foundational stuff to get through. See you next time. If you have any questions or comments, just use the comments on the video. And if you're interested in seeing what's next, please subscribe.